in the case of two independent samples, we have to modify the details of how we obtain p-values. So suppose we have two populations, and using the notation of the textbook, we'll call one of them population A and the other population B, and then each parameter will be subscripted accordingly. So in this situation, we will take random samples from each population. So in A, we'll take a sample of size n according to the textbook's notation. And that means that the random variables we extract are going to be independent and identically distributed, and we don't know what that distribution is. And the important parameter and the important statistic here, I should say, is that we are going to form the population or the sample average. So this will be our estimator of mu A. And from this, we know we can do the standard thing. So as we've done in the course before, we can take the expected value of x bar and the variance of x bar. Now, just like we did before, they are going to be related to the population parameters, but the variance will decrease. It'll be scaled by a 1 over n. Now, in the second population, we'll do the same thing. We'll take a sample of size m. We'll take a independent random variables identically distributed. And again, we don't know what the distribution is, but it's irrelevant. We will form the estimator y bar, and its expected value will be mu b. Its variance will also be scaled accordingly. So now that we have that, in order to compare the populations, we are going to form a new random variable or a new estimator or a new statistic. We will form the difference in the two of them, x bar minus y bar. And just by using the properties of random variables that we've got, we know that if we were to take the expected value of the difference, it will end up being the difference in expected values. And that's just a property of expectation. We'll get mu A, take away mu B. And if we were to take the variance of the difference, because we know that each one of these is independent of each other. So the two samples are independent, not paired. This is going to end up being 1 squared times the variance of x bar plus negative 1 squared times the variance of y bar. And from the work we just talked about, this is going to end up giving us sigma A squared over n plus sigma B squared over m. So if we needed the standard deviation, we could just take the square root of this result. And we are going to need that a little bit later. So note the standard deviation of x minus y bar is going to be the square root of this sigma A squared over n plus sigma B squared over m. So that's going to be an important detail in just a moment. So the key idea now is, what distribution does the difference follow? It will turn out that the exact distribution is not easy to obtain, but it's approximately a t distribution. And that's fine. So we are going to assume that it will be a t distribution. The real headache is, what are the degrees of freedom in this case? So the degrees of freedom turns out to be given by a really awful expression. It isn't something that I want you to memorize, but it will turn out to be based on the strange approximation that is used. Don't worry about where this comes from, but if you're curious, it will be the sample standard deviation of A squared, sample standard deviation of B over its size, so given like that, and then it'll be a strange weighted average of the two. So sample A squared over n squared, 1 over n minus 1, plus sample B squared over M, all squared, 1 over M minus 1. Don't waste any more time worrying about this. In the olden days when they did it by hand, they would just take the smaller of the two individual degrees of freedom and say that's it because it was convenient to do, but it's less accurate. We are going to be using R to perform all of our calculations, so everything here will get automatically calculated. So this is automatic in R. Don't memorize the formula. Don't worry about it. We will never use it. So the idea now is that we can perform the same inference procedures as before. We can do a confidence interval. We can do hypothesis tests. Because the formulas are somewhat overwhelming in the way that they appear, it's good to think about this stuff in its simplest form, right? In the simplest way of thinking of it, you can try to understand what these formulas are and where they come from and what they're going to look like. We are going to form a confidence interval for the difference in these two population means. It's always going to be our estimate minus the margin of error and our estimate plus the margin of error. That's how it's going to look there. The estimate will be the difference in the sample means, and the margin of error is going to be built up the same way. Now, the margin of error is going to be constructed by using a critical value, a T star, that corresponds to the confidence level. Now, we need the standard error. So the standard error turns out to be, by definition, the square root of the sample of the variance for this estimator. So it will turn out to be that quantity that I wrote down a little bit earlier. It'll be sigma A squared over N, sigma B squared over M. That'll end up being the standard error. The one key idea is that we don't know what these are, so we're going to have to replace them with the sample variances. So it will turn out that the margin of error is going to have this form: T star sample A squared over N plus sample B squared over N. So you'll get a really ugly looking expression, but it fits the form that we were given before, right? It fits the form that we will have our point estimate and our margin of error to stick our arms out. So that isn't so bad when you think of it this way. Now, for the hypothesis tests, we are always going to make some sort of null hypothesis, some sort of statement about the difference in these two. And the null hypothesis is the 0 is meant to imply nothing, no change. So this will be the no difference scenario. The alternative will be that this difference will either be less or greater than 0, or simply not equal to 0. The T statistic will be the difference in the sample averages, subtract the difference in the hypothesized population averages. This part will always be 0 because your hypothesized difference is always 0. And then you have to divide by the standard error. And in our case, the standard error is just like we had before. It's the standard deviation of your sampling distribution. So once you've got this, the procedures are identical to what we did before. We are always going to use R to perform this kind of test. If you want to do this, you use the t-test function. Your confidence intervals, just like we did before, you're going to put data set 1, data set 2. You're going to tell it the confidence level as whatever value you'd like. So that's pretty straightforward, nothing more required. If you want a hypothesis test, we are going to go t.test as before, x, y. You can put your value of mu if you don't want it to be something other than 0, but generically it will default to 0. You're going to have to put your alternative, and remember that it's always relative to x. And the important thing here is that we are going to have to put the flag here, paired equals false. Now, this is the default. So if you don't put this in, you will be fine, and you will automatically see that you'll get a strange degrees of freedom that is some strange decimal. So we will proceed like that. Now, one little note, you might read through the book, or you might see some stuff online when you read. We are going to ignore anything to do with pooling the two data sets. Pooling the data sets means you're assuming that the two population variances are the same. We really don't have any justification for the most part to do this. So we don't bother with the pooled option. It's automatically ignored when you go through and you do the tests in R. So as an example of this, I want to go through the logging example on the sheet. So we're going to measure the number of different tree species. So we're looking at diversity of tree species on plots of land that are logged and then unlogged after 8 years. And so the data is given on the PDF file. And if you just take a quick scan of the numbers, you could do things like make a stem plot or a box plot to get a visual of how these look. And you might be able to suspect, you might be able to see that there could be a difference in the mean number of species. So in part A, what we're looking for is a 90% confidence interval for the difference, mu A minus mu B. Now let's take mu A to refer to unlogged and mu B to refer to the logged plots. It's completely up to you which you choose. Whichever one you choose is fine. Just remember that when you get to a hypothesis test, you have to make sure that you're talking about the correct direction. So in the sense of a confidence interval, you are trying to estimate the following, right? By saying, let's take the difference in this 2 plus t star times the quantity with the square root, x bar minus y bar, subtract t star quantity with the square root. In a 90% confidence interval, remember that we are essentially saying, here's the sampling distribution, and I want the area in the middle here to be 0.9, and that means each tail area is 0.05. So problems like this are almost required to use R because the degrees of freedom that you will end up getting is very strange. And so in this case, you can type this data into R and it will spit out interesting values for degrees of freedom. Here, the t value ends up being 2.1141. And so what we're going to do is just go ahead and build all the quantities that we need. So we just follow this formula. Doing this by hand or the long way using R as a calculator is very annoying because you're going to have to calculate each of these quantities directly. It's not a lot of fun. So for the most part, you are going to be seeing all of this stuff in R. And from R, the confidence interval that we end up getting is 0.6517 with some change up to 7.015. And so this is the 90% confidence interval for the difference. Written another way, right? If I just explicitly write this out, we will have unlogged minus mu logged 7.015. What's important to notice here is that the confidence interval does not include 0. That means 0 is not one of the options for the difference in the two. So it is not plausible that there is no difference in the number of species. Here, what we are finding is that it's a positive value. Since all the numbers are positive, this suggests that unlogged has a greater number of species than logged. And that's what a quick sampling of the data will also do. If you just scan through the data sets, you can see that the unlogged plots have a greater number. Now, if we want to perform a hypothesis test, we have to state the null and alternatives, right? So the null is the no difference. That unlogged minus logged is 0, so no difference. Whereas the alternative is what we suspect is the case. We suspect that unlogged minus logged should end up being a positive. We suspect that there are more species, more diversity on the unlogged plots rather than not. So this would be a right-tailed test, and that would mean that the null is really less than or equal to. Because remember, what we're trying to do is separate or partition this up into two portions. Running a hypothesis test, the goal is to try to show you that by taking sample evidence, you have to reject the null. So the sample evidence here is that I would like to compute the difference in the two sample means. If I compute the difference in the two sample means, I can get a whole bunch of different values. But as always, it's much better not to do this by hand. And in fact, I'm going to recommend that you don't, and I'll try to give you problems that you don't have to do this by hand. But if you ever did, this is the idea. So just spitting out some of these values, again, R can be used as a calculator to do all of this stuff. What we're going to do is we are going to standardize. The degrees of freedom is about 14.79, and that comes from just performing the test here, or performing the calculation in R. We are going to standardize. The T statistic is going to be X bar minus Y bar, mu A minus mu B, divided by the square root of sample X squared over N plus sample Y squared over M. The idea of this being the same as always, we are going to assume that, okay, the null hypothesis talks to this problem in as the same way it always does. we are going to assume that the null hypothesis sets the center of the sampling distribution and the center here. And then we're going to say, okay, take a sample. Take a sample from our data. We get a sample value of about 2.11. So again, you can plug all of these numbers into there and end up getting about 2.11. This is something that R will calculate for you. Because this is a right-tailed test, we are asking the question, what's the chance that I would see a sample with these statistics if the center of the distribution really was at 0? And if we go ahead and we calculate this, we would get 0.02596. And so, as with every hypothesis test, this is telling you that, look, if the center of the distribution really was no difference in the population means, you should expect to see a sample with numbers like this about 2.5% of the time in the long run. So if you kept repeating studies like this over and over and over and over again, about 2.5% of the time, you would get results like you got here. And so that means you need to make a decision. Is the sampling distribution, is the center correct? Is the null hypothesis value correct? And did I just happen to get a rare sample? Or is this sample evidence indicating to me that, look, this is too rare to have occurred by chance? It more likely means that the center of the distribution is in the wrong spot, and it probably should be higher. This is where the significance level can assist you. At the 5% level, what we would do is we would reject the null hypothesis because the p-value is less than alpha. Remember that this is the p-value right here. At the 5% level of significance, this is too rare. It's rarer than 5% of the time. But if you are in the logging industry, you are going to lobby for a much stricter significance level. At the 1% level, we cannot reject H0 because the p-value would be bigger than alpha. That doesn't necessarily mean you believe it or you expect it to be true. You just can't find enough evidence or strong enough evidence to reject it. Okay? So in this case, it's not too rare at the 1% level. So you have to be really clear. You have to decide this significance level ahead of time. This is something important. You don't want to cheat and perform your inference procedures and then set the significance level, right? Now, the final thing here was in part C. Loggers were unaware that the effects of logging would be studied. Why is this important? One simple answer: bias. Not the technical definition we used earlier, but the practical idea, right? If you tell loggers ahead of time that, hey, I think your job is a bad one, it's bad for the environment, bad for tree diversities, so we're going to go in and measure the number of species that are left on the plots here. They're probably not going to log a lot of different trees. So you can't bias your results ahead of time. Now, I'm hoping that these examples here have given you a good sense of how to proceed for two sample inference problems for the mean. It's essentially tricks to collapse it down so that you can still use the t distribution. All you have to do is analyze whether pairs are appropriate or independent samples are appropriate.